Alright, hello everybody and welcome back to another video. In today's video, we're going to be looking over problem C, Palindrome Basis. And so for this problem, you're given a positive integer n, and we firstly define what a palindrome is. Palindrome is essentially a number which remains the same after reversing the order of its digits. And so that should be pretty obvious. You want to find the number of ways to express n as a sum of positive palindromic integers. Two ways are considered different if the frequency of at least one palindromic integer is different in them. For example, 5 equals 4 plus 1 and 5 equals 3 plus 1 plus 1 are considered different, but 5 equals 3 plus 1 plus 1 and 5 equals 1 plus 3 plus 1 are considered the same. Formally, you need to find the number of distinct multisets of positive palindromic integers, the sum of which is equal to n. Since the answer can be quite large, print it modulo 10 to the power of 9 plus 7. Which is just 10 to the 9 plus 7. So this problem is essentially asking us to find the number of ways to express a given integer n as the sum of palindromic integers, and order does not matter. So you may recognize this as sort of like a partitioning problem. We need to partition n into different sizes, different group sizes. One of the things that you may note is that we're only allowed to have groups of size k where k is a palindrome. So what can we do here? Well, ordinarily what you would do in a regular partitioning problem is create an array of n, and in that array of n you would go through each number and just add and see if you can get the desired output. So what I mean by that is ordinarily, for example, for 5 you would have an array sort of like, that's not what I wanted to do. You'd have an array, let's use the line tool here, right, like this. There we go, that's a bit better. You would have an array like that, and it would probably be something like this. And so what you would have in that array is you would have some, let's say you'd have 1, or rather we'd start off with 0, then we'd go to 1, then to 2, then to 3, then to 4, and then to 5. So what you would do is you would note that there is a 1 here, because there's only one way to get 0. And then you would note that, alright, let's start with 1. We can add, well, there's currently one way to get 1, so there is one way to get 1 here, one way here, one way here, one way here, and one way here. Right? Now, next what we would do is we'd go with 2. So we'd start from 5. 5 plus 2 doesn't give us help. 4 plus 2, again, that does not help. 3 plus 2, we get to 5. So now we have an additional way. If I were to just, that's not what I wanted to do. Just take that and delete that. And we will clear this selection. So if I were to do that, I would get this to be, let me just see. Okay, so now we've added this to 3. So now we take a look at 2. Can take this, delete, and go down to the brushes again, and make this, and this actually, this should not be 3. This should be 2. And then this should also be 2 as well. And now if you take a look at 1, well, we can change this to be 2, right? And we can change this right here to be 3. Now, why am I changing this here to be 3? Well, that's because what I'm doing here is I'm saying I can have a 1 plus a 2 plus a 2 to get here. Now you might be wondering, well, how do you know you haven't already done that before? Like, for example, I could go from 3 plus 2 to get to 5. But with 3, it's 1 plus 1 plus 1 plus 2 to get to 5. That's where we got that from 3. So that's why we do this. And if I were to continue through the entire thing, you would note that from 0 we just directly can get to here. So let's actually go through and erase these this time. You could get here, and you could do this. And so that would give us 2 here, and what this was, that should be 3, I think. Yeah. So that's our final array. But we've only just done it for 2. Now we need to do it for 3. And then we'll need to do it for 4, and then 5. And so what you can see here is over time we're building up the number of ways to get to n, which is right here. And let me use a different color for this. To get to, oh, that's not the color that I wanted to use. To get to n, right here, using, well, currently the first 0, 1, and 2 possible integers. And then we'll go on to 3, that was a bit dark, 3, and then 4, and then 5. And so that will give us the total number of ways to get to 5. Now you might be wondering, okay, well, how does this help us? What can we even do from here? Well, what we can do from here is we can simply, instead of taking 1, 2, 3, 4, 5, 6, all the way to n, we can take only the palindromes, because we can only use the palindromes. And if we do that, you might notice that we've essentially solved the problem right there, because we've done the partitionings only using palindromes. So that's exactly what we're going to do. We're going to first get all palindromes. We're going to generate all palindromes, right? And once we've generated all the palindromes, we're just going to create the array. And once you've created the array, we're just going to implement partitioning algorithm. Now, you might notice that this would run in the number of test cases t times n times p, where p is the number of palindromes. And if you were to calculate p, I think you'd get it somewhere around like 400-ish. I think it's about 400 palindromes. So you might feel like that's a bit too much, because that's 400 times 4 times 10 to the power 4 times 10 to the power 4, which is like 1,600 times 10 to the power 8, which is way off the charts. That's too much. So what can we do to reduce this? Well, notice that the number of palindromes, the number of partitionings it takes to generate n is static, always. So what we can do here is we can just create our array, something like this, right? And in each spot, we can simply query that spot for our answer. So that's how we're going to do it. We're going to create this entire array beforehand, and for each test case, we're going to query the n from that test case. So that's exactly what we're going to do. So let's go ahead and rewrite that. We will iterate over test cases and query for answer. And that's exactly how we're going to do it. So let's get to work on implementing this. So first, what I'm going to do is I'm going to create our C++ file called pb, and we're going to include bit/std_c++.h using namespace std, and it looks like we're getting a bit of a problem, so we're just gonna go to C++, edit configurations. This is a trick you can use if you're getting some problems. Make sure you're using the right compiler, or whatever it's called, and there you go. And then type def long ll. Type def. And then now int main. And since this looks like this won't have a lot of input, I'm not going to really bother with using fast input and output. So now there are a couple of things that we need to do. We need to generate all palindromes. The way that, honestly, you don't need to overthink this. We can just go through each integer less than maxn. So let's define const int maxn is equal to 4e4 plus 5, right? And then const int mod is equal to 29 plus 7. Right? And actually, I don't remember. I don't think this works. This doesn't generate what you want. You have to do, you have to write this out. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 1, 2, 3, 4. Right? There. And this isn't prime. I should probably make that prime. I don't even know if that's prime. It looks prime. It's probably pseudo prime. Anyways, so we have maxn and we have mod. And now we can create our array. Int dp array outside maxn. And that's going to be our answer. So now we need to create some helper functions. So bool is p, and that's going to stand for is palindrome of int n. Int k is equal to 0. And so we need to iterate. We'll take the modulus n and we'll append it to the back of k. So we'll do while n is greater than 0. K times equals 10. K plus equals, or rather if we're taking from the end, we don't want to push back to the end because we're taking from the end. We want to push to the front. So we'll need another one which represents the number of 10 times we have to add. So we'll say int tt is equal to 0, right? K plus equals tt times 10 plus n percent 10, right? And then n percent equals 10. Or rather, n divided by equals 10. And actually, I don't want to directly modify n, so we're going to say int md is equal to n, and we're going to modify md. And then return k is equal to n, right? So that should work. And for the time being, I'm going to output k and n before returning k is equal to n. Alright, so that star is prime, and now we're going to create a vector. Actually, we don't even need to do that, we can just iterate over. So for int I is equal to 1, I is less than, or is palindrome, not is prime. I is less than max n. I plus plus. If is p of I. Now is the magic. We're going to reversibly iterate. So first, step 1, dp of 0 is equal to 1. And now my main concern is we get to a point where the modulus, when we take the modulus at a certain point, is equal to 0. So what I'm going to do is I'm also going to create a bool valid array of maxn. And obviously this is going to start off being false, so we're going to say dp, or rather, valid of 0 is equal to 1, and that'll just give us it to be true. So we'll reversibly iterate to for int I is equal to max n minus 1, I is greater than or equal to 0, I minus minus, and we'll actually create this to be int underscore right here. Actually, let's change underscore to be inc. So for int I is equal to max and minus 1, I is greater than or equal to 0, I minus minus. We need to go through and see if valid of I. And actually, now that I'm thinking about it, if it's 0, we're just going to be adding 0, so we don't need this valid thing. If dp of I is not equal to 0, while I plus we'll set first j times inc is less than max n, dp of I plus j times inc plus equals dp of I, dp of I plus j times inc percent equals mod j plus plus. Right, there we go. And that should be it. Now we will keep going back and back and back and back. Yeah, that should do the trick. And now we can say int t sin t while t minus minus int ends and south dp of n. There we go. Alright, now let's pray that this works. Alright, there we go. $7.73. No, yeah, I was right the first time. When I was originally devising the algorithm, I was right. There we go. There we go. But it used way too much time. I know that it's using too much time, which is not good. So I want to see if I start from 0, I is less than max n and I plus plus. and we do if and we do this. Does this work? Yes, it does. Okay, there we go. So I might have been a bit stupid and overcomplicated things a little bit, but it works nonetheless. So yeah, essentially what I did here is I just realized that when I was going backwards, it's the same thing as just going forwards and letting the next one handle it from there. So yeah, that's exactly what we were doing. That's why we were overcomplicating it, and that's what I've done to fix it. So now we can copy this code. It looks like it runs in time perfectly, just fine, and we can paste it right into here. And it's accepted. Alright, yeah, so that is problem C, palindrome basis. If you want to take a look at the pseudocode, again, it's right here on the screen. If you want to take a look at the actual code, it's right here on the screen. And yeah, so if you guys did enjoy it, please do not forget to like and subscribe. I have almost hit 50 subscribers, so even just one subscribe could help a lot. And yeah, if you do have any other questions that you have, like any other code forces problems or a specific topic you want me to cover, please let me know down in the comment section below. And with that, I'll see you guys in the next video.